I'll start within 5 minutes. Just I'll wait for a few more minutes for people to join. Okay, good evening, everyone. I am Somodip, and I'm handling this course.
Good evening, sir.
Adva- Good evening, sir. I am Shomodip Chaudhary from Indian Institute of Science. I'm currently doing my PhD here at IISc in the Department of Electrical Engineering, and I'll be handling these live sessions for the course Advances in UHV Transmission and Distribution. So 5 weeks we have completed, and this is the sixth week. Uh, I'm trying, since this is a theoretical course, I'm trying to discuss whatever extra concepts, new concepts which might be interesting for everyone, and like that we have continued the classes for 5 weeks. Yes, so first I'll give a, am I audible first of all?
Yes, sir.
Yes, sir.
Audible.
Okay, fine. So I'll give a quick recap of what I had discussed in the previous class, and then I'll continue the class today. Okay. So Mr. Purushottam, you are asking about the examination. So I have inquired it from one of the TAs who is currently handling that. So he cannot give any suggestions like that, but it will be MCQ based questions. Most probably there will be 50 questions, 50 MCQ questions based on whatever is covered in the course. And the level of the questions will be slightly higher than your assignment questions. This is what was conveyed to me, and this is what I'm telling it to you. Fine.
Fine, sir. Thank you.
Thank you. Okay. So coming back to the course, so we were discussing about audible noise. We had solved some problems related to that. What is SPL? We had seen what is the sound pressure level and how is it related to audible noise. Some numericals we had solved, and we had also talked about some n number of audible noise sources if they are connected. What is the generalized expression for the total audible noise? It is given by 10 log base 10 summation of 10 to the power zero point 0.1 ANI. So from that we had solved 2 or 3 numericals. From that we had discussed what is the L50 level, the L5 level. Then we had discussed about the day-night equivalent noise level. That is during the night time mainly, due to the absence of background noise, this audible noise is increased by certain times to account for the less noise. To make it equivalent to the daytime noise, we do a certain adjustment in the equation for the audible noise, and this LDN is given by this formula, and using that we had solved some numericals. And suppose if we have the rainfall during the daytime and the night time, if PD percentage of rainfall during daytime and PN percentage of rainfall during the night time, accordingly, our formula for the audible noise will be modified, and you can see what is the formula, this thing. So we had solved some numericals using this from the L50 level, and all these things we had done. Then we were discussing about another source of another disturbance which might come in this EHV and UHV lines, which is known as radio interference voltage, or RIV. So for that RIV, I had discussed how the RIV is generated. So to understand that, first you need to understand what is the physics behind the breakdown of any gaseous medium. So from that we understood that multiple collisions between the initiating electron and the neutral air molecules basically generates ions and a secondary electron which further collide with themselves to generate an avalanche of electrons which make the insulating medium conductive. So from this, basically, during this collision, the distance between the different particles, basically the electrons and the neutral air molecule, will be very less. And hence, based on this distance, the pulse which is generated due to these collisions, we call it as RIV, or the radio interference voltage. And when the distance between these electrons and the air molecules is very less, we get a very sharp pulse, right? Because of the distance being less, the time will be there will be less rise time, and there will be a delay, and the tail time or the fall time of the pulse, it will depend on the energy content of the secondary electron. So this delayed decay is due to the lower energy content of the secondary electron. So this type of pulse, you can see from for the RIV pulse, there will be two different parts. If we see, one is the rising pulse and the other is the falling pulse, right? So this is my rising pulse, and this part is called the falling pulse. That we had then distinguished between a positive RIV pulse and a negative RIV pulse. Basically, from experiments and from empirical relationships, some expressions are proposed for the positive RIV pulse and the negative RIV pulse. Basically, the positive RIV pulse, we have seen that it is a double exponential pulse. From this equation, we can see. And for a positive RIV pulse, these positive ions will hit the neutral molecules. And since the mass of the positive ions is very high, the rise time and tail time will be higher, because the time required for the collision, it will be obviously higher because of the higher mass, which will lead to higher inertia of the positive ions. And for a negative RIV, the rise time is very small, and that is gradually followed by a gradual exponential decay. So these are all, if you want some derivation for these pulses, how the equations came, that basically these are empirical relations. What do you mean by empirical relations? So empirical relations are certain relations or equations which are proposed based on multiple experimental results. From the experimental results, it has been found that the negative RIV pulse as well as the positive RIV pulse, that is basically given by these equations. So then we had discussed about our RIV measurement circuit. So this RIV measurement circuit has different components. This is the LC filter is there. Then there is the test object for which we are trying to measure the RIV, which is emitting the RIV or the radio interference voltage. So basically first if you see this circuit diagram, I'll zoom in. This LC filter, basically it is present to absorb any kind of RIV signal from the test object. So the test object will emit the RIV signal, right? So RIV signal has two paths. One is the red path shown here, this path, and another second path is this. So my measurement circuit is in the right half, right? So we want the entire RIV signal to travel to the right half of the circuit, and hence we are placing a LC filter on the left half of the circuit near the source, so that the RIV signals, basically these are high frequency signals, right? So these high frequency signals can destroy our high voltage source, the resisting transformer or the Marx generator. So basically to avoid that, we use an LC filter. Then we have the coupling capacitor, and then we have the L, the inductor, and then we have some matching impedances. And as I was telling that this entire RIV, it is dropping across the coupling capacitor CC, which develops an electric field. Whenever any signal or excitation is applied to a capacitor, basically we think it as a electric field, and if it is applied to an inductor, we think it as a magnetic field. This is basically a perception. So depending on the frequency, along across the inductor, a magnetic field will be developed, and across the capacitor, an electric field will be developed. So there will be continuous transfer of energy between this coupling capacitor and the inductor. Due to this continuous transfer of energy, we get a pulse with a certain on time and a certain off time. So this pulse duration gives me the frequency of the pulse, and the magnitude of the pulse will give me the magnitude of the arrival. So the cable is connected. This you can see in this figure that we have connected a cable for the measure. So basically, for any high voltage testing or measurement circuit, if you see, we basically use these cables. So why we use these cables? Any idea, anyone? Why we use this delay cables or cables for measurement in the high voltage circuits?
Impedance matching.
Yes. So basically in the high voltage equipment, any high voltage equipment, we cannot directly connect across any meter. So in our power electronic circuits, which we, or the electronic analog electronic circuits, which we do in our labs. So basically those are some 2 or 5 volts, maximum 10 volts. So that will not create any issue. But a high voltage equipment, it will generate either very high magnitude voltages and currents or very high frequency, both of which are dangerous to my meter. So we connect a cable and a cable from the high voltage equipment to the meter. And basically that is connected by impedance matching so that there is no reflection, because this high voltage equipment, these high voltage signals, high frequency or high magnitude signals, basically high frequency signals, there will be an issue of reflection. We have seen the traveling wave phenomena, right? We know of the traveling wave phenomena. So this any signal we know it, any voltage or current, it travels as a wave, and if it sees any impedance mismatch at any junction, some part of it will be reflected and some part of it will be transmitted. So what we do is basically, suppose there are, this is one impedance. We have a junction here, another impedance. So this is 10 ohm, this is 20 ohm. Say a signal here is traveling. Okay, some voltage signal. So when it comes here, it sees an impedance here 20 ohm and here back 10 ohm. So if V comes here, some part of it will be reflected and some part of it will be transmitted. This is the magnitude of the reflected and the transmitted voltages that will basically depend on the magnitude of this impedance. So basically, if by impedance matching we mean, so here there is an impedance mismatch, right? Because the impedance are not equal. So if I make this impedance as 10 ohms also, then there is a match. That is, this 10 ohm and 10 ohm are equal, and hence there will be no reflection. The entire wave will be transmitted, right? So this is basically the concept behind reflection of the this reflection. So basically we use this impedance matching for impedance matching in any high voltage equipment or any high voltage cables which we connect. We should obviously use an external resistors for matching of the impedance with the cable. So is it clear? Any doubts? Anything pertaining to previous week's class and anything related to the course you can ask. Any question? Anyone?
It is clear, sir. Please, you can go ahead.
Okay. Okay, fine. You can stop me in between anytime if you have any questions. So next we'll be looking at a topic which we call as grounding. Under that, first we will look into substation grounding. Just a second. So first we need to understand two types of signals, right? First is my power frequency signals. which is f equal to 50 hertz. And what is the wavelength for such signals? Lambda is given by velocity of light by the frequency. So this will be 6,000 kilometers. And then we have impulse signals. That is the high frequency signals. So here frequency will be around 1 megahertz. And here lambda is 300. So depending on the signal, we use one term which is known as electrically thin wire. So suppose we have a wire like this. Say this is a pen. I just imagine a normal wire. Okay. So how do we say whether a wire is geometrically thin or how we say that it is geometrically thin? Basically, if the diameter of the wire is less than a particular say 1 centimeter or 1 meter, then we say that it is geometric. We say it is a thin wire. But how means that is geometrically thin. So another concept arises which is known as electrically thin wire. So what do you mean by electrically thin wire? Basically, electrically thin wire means if the length of the uh, wire is less than the wavelength, is less than a particular fraction of the wavelength of the signal. So suppose I have a wire, through it a signal of 50 hertz is propagating. Okay, so for that, suppose I'm telling, just try to understand this thing. This is very important. Suppose I have a 10-meter wire and through it 100 hertz signal is propagating. So what is the wavelength of that signal? It is basically 3 into 10 to the power 8 by 100, right? So it is 3 into 10 to the power 6 meter or 3000 kilometer. Just a second, I'll come back. So sorry for the interruption. And so as I was telling, suppose a 10-meter wire and through it a 100 hertz signal is propagating. So for that my wavelength will be 3000 kilometers, right? So a 10-meter wire in corresponding to a 3000 kilometer wavelength is very small, right? So if I say L by lambda, if I find what is L, 10 meter by 3 into 10 to the power 6 meter. So it is very small, right? So it is 0.33 into 10 to the power minus 5. The fraction is very less. So we can call it a electrically thin wire. Whereas if I have that same 10-meter wire, but the frequency is say 2 gigahertz signal. So what will be my lambda here? It will be 3 into 10 to the power 8 by 2 into 10 to the power 9. So it is basically 0.15 meter. So now you can see this 10-meter wire, if I compare it to the wavelength, so it is more, right? So L by lambda is 10 by 0.15. So it is basically 10 into 10 square by 15. So it is very high. This value is very high. So we cannot call this 10-meter wire an electrically thin wire when a 2 gigahertz signal is propagating through it. Is this concept clear to everyone? Any confusions, anyone?
सर रिपीट करेंगे एक बार?
Yes, sir.
Okay. So the thing is what I am telling, I was talking about electrically thin wires, right? So geometrically thin wire, any structure, we can say it is geometrically thin by looking at the dimensions of the wire, right? So I say that my threshold is say 1 meter. Anything less than 1 meter is thin for me. Any wire whose dimension is less than 1 meter is thin for me. But whether that 1 meter wire is electrically thin depends on the signal which is propagating through that wire. So for that particular signal propagating, I was giving the example of this 10-meter wire. So this 10-meter wire can be electrically thin for a particular frequency of signal, and it cannot be electrically thin for another higher frequency of the signal. So basically, this 10-meter wire for if a 100 Hz signal is propagating through it, the wavelength lambda will be 3000 kilometer. And if we see L by lambda, it is very small. It is of the order of 10 to the power minus 6, right? So that is very small. So we can say that it is electrically thin. Yes, my 10-meter wire is electrically thin for a 100 Hz signal. But that same 10-meter wire, if a 2 gigahertz signal is propagating through it, we are seeing that the wavelength is only 0.15 meter. And the 10-meter wire, the L by lambda ratio is very high. So we cannot anymore call that electrically thin. So is it clear now?
Yes, yes.
Okay. So this concept you first need to understand. And now I will be talking before substation grounding. This was one important, but this has nothing to do with the substation grounding. Just this is an important concept. Just keep this in mind. So basically, in substation grounding, so here we will be talking of this wavelength only, right? For every lambda distance. So lambda is the wavelength of my signal. So after every lambda distance, we will see in this propagation of the signal, we will see a fresh waveform will come. And the traveling wave component of the previous section is adding up to it. So I'll repeat it once again. For substation grounding, we have grounding rods. And for this grounding rods, after every lambda distance, that is after every wavelength distance, a fresh waveform comes. And the traveling wave component of the previous section is adding up to it. So for power frequency, if we see, so this lambda thing is dependent on the frequency of the signal. So if a signal is a power frequency, say 50 Hertz, then this distance is very high. So that this new fresh waveform doesn't come into picture. But for high frequency signals, this lambda is very small, right? And so this concept of this new fresh waveform adding in to the previous section is that builds up the electric field or the any electric signal which is propagated. And we know for an antenna, if we see, so for an antenna, we know there are two types of components. One is called the near field region. For D, this is D less than equal to lambda by 4. And we have the far field region, which is for D greater than lambda by 4. Suppose I have an antenna like this. Suppose I have an antenna like this. This is the so suppose my antenna is like this, a disc. Suppose this is my lambda by 4 distance. This region So all the field lines that are emanating from the antenna, which has influence up to λ/4, this region is known as near field region. And this region is known as. So now we need to understand the behavior of the electric field in the near field region and the far field region. So if you understand this concept, then it will be very easy to relate substation grounding and impulse grounding. So basically substation grounding will be in power frequency, whereas my impulse grounding will be in this higher frequency. So first I'll write the important points, then any confusions you can tell me.
Excuse me, sir.
Hello? Yes?
Sir, normal this grounding is not different from earthing, sir.
No, it is same.
Same, sir.
Hello?
Hello, sir.
Hello?
Okay, sir. Okay.
Is it clear?
Clear, sir.
So for an antenna, which has multiple current sources, there will be mutual induction, right? So due to mutual induction, the field means electric field till λ/4 is of disturbance type. I will tell what is disturbance type of field. And generally, it does not follow Maxwell's equations. Okay. So basically, we know any electric field, the basic governing equation for any kind of electric field, that is a Maxwell's equation. Whereas for an antenna which has multiple sources and due to this mutual induction, the field till a distance of λ/4 from the antenna is of disturbance type and it doesn't follow the Maxwell's equation. So after λ/4, after a distance of λ/4, it follows. So basically from d equal to 0 to λ/4 is my near field region, right? So it follows Maxwell's equations means E is proportional to inversely proportional to the square of the distance and the magnetic field is proportional to inversely proportional to the distance, right? So here E is not proportional to 1 by r square and H is also not proportional to 1 by r. Whereas for d greater than equal to d greater than λ/4, this is my far field region. And here E will be proportional to 1 by r square and H will be also proportional to 1 by r. So now we can see that now I will talk about impulse voltage grounding. So in impulse voltage grounding, so basically this substation grounding has two parts. One is for impulse voltages and another is for this power frequency voltages. For impulse grounding, any confusions, you can stop me in between. Okay. So now this merging of waveforms comes into picture. So now for our impulse voltage grounding, from 0 to lambda by 4, the first impulse starts developing. Okay, the first impulse wave will start developing and it stabilizes as a single impulse wave after lambda by 4. Okay. Since the distance 0 to lambda by 4 is known as this disturbance has a disturbance type of field, so there will be after lambda by 4, this field, this impulse voltage field will stabilize. So now by lambda by 4, the second impulse also starts developing and is about to strike. And this cycle continues. So now can you understand the difference between this grounding for a power frequency voltage? For power frequency voltage, what will happen? The frequency is very low, right? So the lambda will be very high. And this lambda by 4 distance itself will be very high. So even before the second impulse wave comes, this first impulse wave will be stabilized and there will be no issues. But however, for impulse voltage grounding, what will happen? This for impulse voltages, the signal frequency is very high, right? And for that, this lambda by 4 will be very small. And before the first wave stabilizes, first impulse wave, the second impulse wave also starts developing and it is about to strike. And this continues. After another lambda by 4, the third impulse starts and the second impulse wave gets stabilized. So there is an overlap of waveforms. So if someone asks you what is the effective wavelength for impulse grounding? So the effective wavelength is lambda by 4 and it is not lambda. So this you must remember. The effective wavelength hello, am I audible?
Yes, sir.
Okay. So the effective wavelength for the impulse grounding is lambda by 4 and it is not lambda. Okay. So is this clear? Any confusion, anything? So here I have not discussed in details the procedure of the grounding, but I have explained you what is the physical meaning or the physical differences which will arise between power frequency grounding and impulse voltage grounding. So next topic is we will look into the existence of ground loops. So is this clear to everyone? Any doubts? Anything? Can I move ahead?
No, it's okay. Yeah.
Okay.
Question, sir. Then I have
Yes.
some doubts. Be
Yes,
clear.
yes, sure.
Suppose the lightning comes
Hmm.
on a building, and we will have provided a lightning arrestor, and the lightning impulse it will come to the ground, and it, because of the high frequency and the lambda condition, where we have this multiple, the wavelength it is repeated, multiple pulses will be there, and the ground potential will increase. And suppose a person walks around that particular place, where it is grounded, the step-in voltage will be more, and a person will be electrocuted.
Yes, there are chances. Yes, you're correct. There are chances of getting electrocuted.
Therefore, we may have to give a very low impedance so that the ground voltage is very low.
Yes, correct. We have to provide a low impedance, low impedance path for the this lightning impulse wave.
Thank you, sir.
Thank you. So now we'll be talking about existence of grounding loops. Okay. So I'll draw the schematic first, then I'll be explaining. Okay. So suppose these are two equipments, okay, which are grounded. This is my equipment one. This is my equipment one, and this is my equipment two. And these are grounded through some inductances. So this is the resistance of soil. Okay. Suppose I have two equipments and there is a fault in equipment one, and as a result of which a fault current IF passes. So what will happen? This is called a grounding loop, right? So this creates a loop. We have the connections here also. You might think that there can be issues in the how is it completing a loop? Just ignore this part now. So now you think, suppose there is a fault in this equipment one. Okay. So any fault in equipment one, so that generates a fault current. A fault current IF, which passes through equipment two, right? And hence it energizes this equipment too. And hence it creates a separate fault So basically what is happening, any fault in equipment 2 that is generating a fault current IF, which flows through the soil into equipment 2. And this energizes equipment 2 and hence it creates another fault. So this is not desirable, right? Because we had designed this grounding, the ground loops for mitigation of the fault. So rather what is happening, another fresh new fault is happening in another equipment, which is this equipment one and equipment two can be separated by distances, right? So that is creating another fault. So thus we can say that there is effectively there is a propagation of fault current among the so there is a propagation of fault current among the two equipments. So the general advice which is given to the linesmen or the line engineers in the substations, while grounding, you should try to avoid these grounding loops. So grounding loops must be avoided. Or means how you will avoid these grounding loops? You have to break these loops by very high resistivity, some materials of very high resistivity. Some equipments, like in the soil only you have to do this, like gravel having very high resistance. So if you give a very high resistance in between, so this fault current will not propagate to the other equipment. So this type of grounding loops is very dangerous for electronic equipment, especially. So this is dangerous for signal grounding. Especially. So moreover, one more thing we have to keep in mind, like we should never ground ever ground power equipment like a transformer with the signal components in the control loop. So they should not have a common ground, because the very high current, any fault occurs in the transformer, that can cause damage of the signal component because their voltage withstand capability is very less. Right. Just a second. I'm audible, right?
Yes, sir.
Fine. So this thing is clear. This ground loops. Any confusions? Any doubts? Why we should avoid resistance? Why we should avoid ground loops and all? Is it clear? Any
Can I have
confusions?
one more?
Yes,
So
yes,
this is
sure.
the reason why we are putting gravels in a substation. Where the
Yes, yes.
transformer equipments are there, where the switch gear and everything.
Yes, you're correct. This is the main reason why we are putting gravel to provide a high resistance path, because while grounding, these equipments will be anyhow connected. You cannot avoid the connection between the equipments through the soil, but you can break these ground loops by placing some high resistivity materials like gravel or soil, something like that. Yes, you're correct. Anything else? Any clarification?
सर अभी मोस्टली अभी अर्थिंग ग्रिड वापरते हैं, तो उस सिचुएशन में क्या होगा?
अर्थिंग ग्रिड, यस, बोलिए फिर से रिपीट कीजिए तो।
अर्थिंग ग्रिड इंटरकनेक्टेड अर्थिंग रहता है जगह। तो उस सिचुएशन में क्या होगा?
That is different. So that I'll be discussing. Just wait for this earthing mesh you are telling of, right? Earthing grid bol raha hai. That is different. That thing is different. I'll tell. Next topic is that one only. So now we need to look about before designing this. There are different kinds of grounding equipments we can use. Like there'll be rods, grounding rods or earthing rods. You can have grounding mesh. Then you can have a Faraday cage like structure, or you can have plate grounding. So before we consider this, before the design of this, we need to understand the properties of soil. We need to understand what is soil made of and what are the different properties of soil, what makes these properties of soil, how we can use that, and how the behavior of soil is different for different frequency signals. Like for it can behave the electric field which is created due to a particular signal inside the soil, that will behave differently for different frequency signals, right? So for that, we need to understand the properties of soil. So next I'll be talking about basically soil properties. So what are the parameters we look into for soil? While from the electrical perspective, if we see parameters which are considered for soil. First of all, we see percentage of water that basically determines the conductivity or the resistivity of the soil. Next, we can talk about resistivity. Then we have magnetic permeability. These are all the material properties. Okay. Is given by rho soil. Then we have mu soil. Then we have the permittivity. Silence. Okay. So first, I will talk about this impulse voltages, right? Suppose you have, this is my ground level. Another is the so this is my E vertical and this is my E horizontal. So what is the resultant? We will have the resultant something like this. This is the E net. So when this lightning voltage strikes the ground, so why there are two components? Why not a single vertical component going down? Because there is in the soil, if you see, it is considered as a multi-dielectric medium. So since there is a change in the medium, the field will deviate at each stage, at each layer of the soil, wherever the permittivity changes significantly. So there the field will deviate and we will have a net propagation of the electric field in a particular direction. So I'll write that. When a lightning impulse voltage strikes the ground, field deviates due to. So later you will see this change in medium that is also dependent on the frequency of the signal, because you know that permittivity, as we say epsilon, if we go for high frequency signals, we see that epsilon has two components, real component and imaginary component. So you might not have heard of this. So epsilon is also a frequency dependent component. You should keep this in mind. So for basically we deal with signals in power frequency, we electrical engineers basically deal with power frequency signals. So we basically consider epsilon as a constant, right? But that is not the case. It will depend on the frequency of the signal. So if it is a very high frequency signal, obviously epsilon will be dependent on the frequency. And since there is dependence of the epsilon on frequency, depending on the whether it is an impulse signal or a power frequency signal, the behavior of soil will be different. Is it clear? Any confusion? Is it clear? Behavior of soil is dependent on the frequency of the signal that is propagating. It's clear, right, madam?
Yeah, yes.
Okay. So first you should keep this in mind. So the next thing which comes, just I'll write about the field behavior. So we are having two components, right? One is the vertical component and the another is the horizontal component. So the vertical component directly penetrates into soil, whereas this horizontal component passes through different interfaces and undergoes multiple deviation. Okay, so due to this, soil gets polarized. Polarization, all of you have studied, right? You know what is polarization. So basically, due to this deviation and different layers on the soil will get polarized, and mainly, so we have different kinds of polarization, right? Ionic polarization, interfacial polarization, then we have Debye polarization, and it mainly undergoes ionic and orientation polarization. So polarization in itself is a huge topic. Since time is limited, I cannot discuss. So this polarization also creates many problems. So we need to ensure that the soil in between the two rods, now we are focusing on say rod type of grounding, right? Should be purely resistive. That the soil between two grounding rods should be purely resistive. And this rod should be inserted at a particular depth only to avoid the propagation of the horizontal component. So as I was telling, this horizontal component, it passes through different interfaces and undergoes multiple deviation. So to ensure proper grounding, we cannot allow this. We should ensure that the propagation of the horizontal component is minimized as far as possible. So, so the basic funda behind this is that this soil, the behavior of soil is a frequency dependent phenomenon. Is it clear? Behavior of soil is a frequency dependent phenomenon. For high frequency, it can behave as a multi-dielectric medium, and which is very complicated for analysis. But generally, for power frequency voltages, it is assumed as a uniform strata. That is single media we assume. Because for power frequency, this epsilon is almost constant. So is this clear to everyone? Behavior of soil and the propagation of the horizontal and the vertical components. Is it clear? Any questions, anyone?
So do we
You are
have
giving the
any,
vertical, yeah, please.
Yes, you can continue, Dr. Vansala.
You are giving the vertical and horizontal, but other than that, with the angular displacement, any slanting way or only two directions?
Yes, basically any wave which is propagating. So this is my actual direction of propagation. This one. You can see in the screen. 1 second. This is my actual direction of propagation. This is the actual direction
Oh,
of
right, right.
propagation, and we are
You're
resolving it for analysis.
Solving,
We are
okay, fine.
yes, we are resolving it into the vertical and the horizontal component basically for
Okay, okay,
analysis
fine,
part.
fine.
Yes, Samir, you can ask.
Yes, sir, does soil thermal resistivity also play an important part in?
Yes, can you come once again? Once again, can you repeat your question?
Yes, sir. I'm saying the soil thermal resistivity also has any part in grounding properties of
Yes,
soil? Thermal
soil
resistivity.
thermal resistivity. Uh, yes, as far as I can think, thermal resistivity. I think 1 second. Thermal resistivity, basically that is quantifying the flow of heat. So here actually, yes, for lightning impulse voltages, if the magnitude of the impulse voltage is very high, then yes, obviously some heat will be generated. And yes, the thermal resistivity property to some extent it should affect. It should govern the process of grounding also. Yes.
Right.
Anything else? Anyone? Any questions? Fine. Okay. So next, this grounding is completed. Some important topics I took basically. So next we will move on to the generation and this measurement of high voltages, which has been discussed in the course, yes. But I'll give a brief intro first, and then will will go into the detailed thing. So anyone is familiar with the generation of high voltages in the laboratory for testing purposes? What are the different mechanisms? Anyone? Anyone has any idea?
Some cascading of transformers.
Yes. So basically we have three kinds of voltages in the which we in if we are talking about normal power frequency voltages, we have only DC and AC voltages, right? Whereas for this high voltages, we basically have three kinds of voltage. One is DC, then we have AC and impulses, right? So impulse, it is neither DC nor AC, right? It is a very high frequency voltage, which has, this is basically an impulse voltage, which has this is the rise time, and this is my fall time. This is the 50% value. This is B. So this is basically my impulse voltage. So in that, first I will talk about the generation of AC voltages, AC high voltages in the laboratory. So I will describe all the methods of AC voltages. I'll do some numericals also, and I'll give you some assignment problems. Try to solve. That is not for submission, but that is for your betterment only. Okay. So those who are interested, they can go through that. So first we have the cascaded transformer. Next we have series resonant transformer. Next we have the Tesla coil. Have you heard of this different mechanisms? Tesla coil, I think everyone has heard, right? Anyone has heard of these different methods of generation of high voltages? Hello? Hello, is it audible?
Yes, sir. Audible.
Okay, so one second, just a second. Okay, so we have basically three ways, the three different methods of generation of cascaded for is high AC voltages in the laboratory. We have the cascaded transformer, we have the series resonant transformer, then we have the Tesla coil. So any idea, anyone has ever read of this? How these different methods, what is the principle? Any idea? So just a question, how is this Tesla coil circuit different from the voltage that is generated by Tesla coil? How is it different from the other two? Any idea?
Sir, if I remember cascaded transformers, I think this there will be a three-winding transformer, and the third winding it will be connected to the the primary of the second transformer, and the second transformer's tertiary winding will be connected to the primary winding of the next transformer. I think,
Yes, you are
I'm not
correct.
sure of it, but it may
Yes,
be like
yes.
that.
It is not a three-winding transformer. It can be four-winding, five-winding means five stages transformer also. Yes, it is a three-winding transformer. The winding, there are three windings. We have the primary winding, the secondary winding, and the excitation winding, right? So, okay, I will draw the schematic first, then you can understand. Just a second, Mr. Raju. I think my earphone has gone bad. Am I audible now?
Yes, sir. Audible.
Yes, audible.
Okay. Okay, so as Mr. Raju correctly pointed out, yes, the cascaded transformer, that is a multi-stage three-winding transformer. And using that, we generate the high voltage. Basically, we apply a voltage and based on the number of stages, that voltage is magnified. Okay. So first I will try to draw the diagram. I'll see if I can accommodate here. The diagram is big, very big. Just give me 5 minutes. I will draw that. Then I will explain. So this is basically a three-stage cascaded transformer. Okay. Is the figure visible to everyone? Okay.
Yes, sir.
Okay. Fine. So here, suppose this is my first transformer, and there are three different stages of the transformer, right? Basically, if you see here, this is my stage one. This is my stage two. And this is my stage three. You can have n number of stages of a transformer, of the cascaded transformer. The different stages are clear, right? So you have to follow this with me, otherwise you will lose the track. Is it clear?
Yes, sir. Following.
Okay. So suppose I am applying an input voltage of say V volts. Okay. So if this is V, I suppose I have the ratio of the transformer is say V is to Vi is to Vi. Okay. So suppose this will be then Vi, this voltage will be Vi. So if this is Vi, obviously across this winding, the voltage will be Vi. Right. So again, I have V is to Vi is to Vi. So this is again V, this is Vi. Then if this is Vi, since it is directly galvanically connected to this winding, this will be Vi. And if this is Vi, again the ratio is V is to Vi. So this is V. And these red things you can see, right? These are the insulating stands. So basically, first you think that there is no insulating stand. So the voltage at this point is V, right? So this V cannot be directly grounded. We have to give an insulating stand of V volts so that we have to give an insulating stand of V volts. And here you can see we have to give an insulating stand of 2 V volts, right? So if we give an so here the voltage across this point is V, then we have 2V. So what is the output voltage across the test object? It is 3V. So basically we were giving an input voltage of V and we are getting an output voltage of 3V. So this is basically magnification of voltage. That is general general technique of high voltage generation. Okay. So now if you see the power ratings and the current ratings, then you will understand. Suppose this has a power rating of say P. Okay. If this is P, this P is fed by this, and this. Sorry, this P is being is supplying power to this winding and this winding. So basically, based on the ratio of this will be basically 2P by 3. This will be basically P by 3. And this, since this is 2P by 3, this will also be 2P by 3. And this 2P by 3 is being fed by two transformers, two windings. So this will be P by 3. This will be P by 3. If this is P by 3, this winding also has a power rating of P by 3. And this P by 3, so this one is also P by 3. So the last winding has a transformer output rating of P by 3 watts. So basically, the input power capacity of the cascaded transformer is P watts. Then we have the output rating, the output kVA rating will be P by 3 watts. And now, if you see one more thing, if we now see the current ratings, just a second. So suppose a current of 3 IK is flowing here. K is the transformer ratio. Okay. So if 3 IK is flowing here, this 3 IK is being generated here, it will flow 2 IK. So this 2 IK and here it will flow IK. This 2 will make 3 IK. So this 2 IK will be here, it will be IK, here it will be another IK. So this will transfer to 2 IK. And this IK, since the ratio is K, here it will be I. So now you can see what is the input KVA rating. What is the input power? Input KVA equal to P, that is equal to V into 3 IK. So it is 3 VIK. Okay. What is the output power rating? This is the input KVA and the output KVA, that is P by 3, right? Sorry. It is the output voltage 3V into the output current, it is 3 VI. So there are 3 windings in each transformer, right? So this is my primary winding. This is represented XP. This is my secondary winding. This is represented as XS. This is my excitation winding. This is XC. Similarly, for the other stages also, we have XP, XS, and XC. So is the explanation clear? Any confusions, anything? Sorry, this one I have written incorrect. This current will be I. So HV winding, so primary winding is carrying 3 IK current, 2 IK is being carried by excitation winding, and each of the HV windings carry a current of I equal to P by 3, P by 3V. So I will write this point. Each of the HV windings carry a current of I equal to P by 3. 1 second. So each of the HV windings is carrying a current of P by 3V. Any confusions, anyone? Any doubts? Any doubts, anyone? I'm audible, right?
We can go ahead.
So you can see some of the important conclusions from this. The primary winding of the first transformer, that is the first stage, supplies the full power, right? Full power P. So that is one of the concerns which we need to think in the design stage, that is heavy loading of the primary and the secondary windings. This is one of the factor So this factor has to be considered in the design stage. Okay. Is it clear? So now we can derive an expression for the reactance, the equivalent reactance of this cascaded transformer. So first we will look into, before that, we will look into the advantages and the disadvantages. Advantage is simple. Circuit topology, and the disadvantage is, as I had told, first is heavy loading. At the lower stages. And then also this procuring this insulating stands.
Can you repeat the first disadvantage?
And the first disadvantage is the heavy loading at the lower stages of the transformer, because you can see from the figure here that you can see the power rating of the stage 3 transformer is only P by 3, whereas the total power rating of the primary of the first transformer is P, that is 3 times. So at the lower stages, that is, suppose if you have 7 or 10 stage, so basically there will be a difference of power of at least 7 to 10 times, right? So that is a heavy loading is present in the lower stages, and that is a factor which has to be considered in the design stages. So that is one of the disadvantages. And the second disadvantage is the procuring the insulating stands of high voltage ratings are not easy. Means getting this insulating stands of that much high magnitude voltage is not always easy. Okay, so these are the advantages and disadvantages. Now we will derive an expression for the equivalent reactance of the cascaded transformer when referred to the primary side, HV side. Okay, so for that, a small derivation I will do, just look into it. So last half an hour, 5-10 minutes, I will complete. Last half an hour, I'll take some questions or suggestions from you. The last 2 weeks are remaining after this. So any topics specifically you want to learn, you can tell me. Anything related to electrical engineering. So I'll do this derivation first. So let us assume that XP is the reactance of the primary winding. XH is the reactance of secondary winding. XC is the reactance of the third winding, that is the excitation winding. Let us assume K is the turns ratio. All we are doing for one stage, okay? So now if you see what is the total power loss? It is basically summation IN square XN. So here we are trying to derive the reactance when referred to the HV side. Okay. So any reactance, any transform you have studied in the electrical engineering, that any reactance we can refer to the we can refer it to a particular HV side or LV side, high voltage side or low voltage side, and we can determine what is the equivalent reactance, right? So basically we multiply Now you will see. Okay. So total power loss, if I say it is I square into, so basically power loss is I square into X. So we are saying I square into X HP. So this is equal to the total power loss, right? So for the first stage, what are the different currents? So it is for the primary, the current is 3IK, okay, plus XH into, you can look at the figure, okay, plus XC into 2IK whole square. Then we have second stage. So it is I square for XH plus KI for XE, and we have KI for primary. And for the last stage, we have only I current, right? So if you sum this up, you can see it is basically, and if you cancel this I from both sides, it is basically 14K square XP plus 5K square XC plus 3XH. Is it clear? So this is the reactance of three-stage cascaded transformer referred to the HV winding. So this we have done referring to the HV side. So if we were to refer it to the primary side, so we have to then refer all the windings, all the currents to the primary side. Is it clear?
Here, one more doubt, sir.
Yeah, it's okay.
Now, the total power loss means it cannot be a reactance. I squared
Yes,
into
correct.
it will come.
Can you? You're not audible, sir. Can you come once again?
Sir, power loss, if you are taking it, therefore I squared into reactance will not be there. I squared into R, the resistance will be there.
So basically, this is impedance. I told
Impedance,
reactance. It is basically impedance.
But the impedance out of which the reactance part of it, it will not contribute. It will be contributing only the voltage drop. Whereas
Yes,
the power
correct.
loss,
That,
if you are taking it, only the resistance will take care of.
yes, obviously. Power loss, obviously, because the reactance will take care of the reactive power, right? Yes, you are correct. So basically, we refer it as reactance, but power loss, basically, it is, yes, it is the resistance part. Is it fine? Is it fine, Mr. Raju? Hello?
Correct, sir. Okay, sir. Thank you.
Oh, okay. Anything else? Any confusions? Now, last half an hour, you have to ask some doubts. Some 15-20 minutes we can spend. Any questions, anything you can ask? So I can see some new participants today, I think. Vinod Kumar, Mr. Vinod Kumar. Mr. Vinod Kumar. Yes, Samir.
Hello?
Yes. Can you speak a bit louder?
Yeah, yes, sir.
Yes.
Sir, actually, I was going through the weekly course. Sir, in one area, it is mentioned that the circuit breaker uh, has the property of detecting a fault. So, can you please elaborate it? Because as far as I know or seen practically, that CTs and VTs are the devices which detect the fault and they relate to the circuit breaker for tripping. So can you please check or can you please
Your voice
elaborate?
was breaking in between. The first line, what you told, can you tell once again?
Sir, the thing was in the videos we have seen, it is mentioned that the circuit breaker also detects a fault.
Hmm.
But as far as actually I remember, it is the CTs and VTs in the circuit which detect the
Hmm.
fault,
Hmm.
fault current or over voltage, and then they relay this to the circuit breaker for tripping.
Yes, correct. Okay, so you want to know how is it detecting the fault, right?
Yes.
Circuit, basically the work of the circuit breaker is to trip the faulty part, right? So it has to detect the fault first and then only that tripping will work. So basically circuit breaker will not do that detecting part. That will be done by, I think, some sensors and all will be present, which will send the
It is
trip signal to the
it's the
circuit breaker.
circuit is CTs and
Uh,
the potential transformers.
yes.
They detect the over voltages and over currents.
Hmm.
What my doubt is, instead of CT over voltage and over current, does the circuit breaker also have any other protection? What do you say? Protection scope.
No, what else protection scope will be there? Only over voltage, over current. These are the two types of faults which can be
Yeah.
detected by the circuit breaker, right?
So, sir, so can we say that the circuit breaker detects a fault?
Technically, it is not correct to tell that detects circuit breaker will not actually detect the fault. So there is a separate trip unit that is CT and CT you were telling.
Yes.
So that
Yes.
will instruct the circuit breaker to trip, and that circuit breaker will just perform the action of tripping. It is not exactly correct to tell that circuit breaker is detecting the fault. So one thing you can do, you can share that part of the video where you have the doubt and you can post it in the forum. So basically
Yes,
our
sir.
TA
Yes,
is
sir.
looking into every question. Okay.
Okay, sir.
I also look into that. Some of the questions I also reply
It's,
there.
it's in the substations part, the first part.
Okay, okay, fine. You can just post it in the
I will
discussions
post it.
forum.
I will post it, sir.
Okay.
Also, sir,
Uh,
one more doubt. Actually,
Hmm.
I was going through the overhead grounding optical with optical fiber.
Hmm.
Sir, actually, whenever there is a high current,
Hmm.
sorry, not the high current. Whenever there is a flashover or
Hmm.
the lightning strike on the overhead ground part,
Hmm.
there will be some heat also induced in this wire.
Yes, correct.
So this heat will it not disturb or interfere with the communication which is going through the OPGW, the fiber optic inside the ground wire?
The heat, how will the heat interfere? I could not. Two signals can cause interference, right? Heat is not a signal. How you are telling? Can you elaborate?
No, sir. What I'm saying is there will be a tremendous amount of heat which will be induced at that moment in
Hmm.
the ground wire
Hmm.
when there is a lightning strike.
Hmm.
So this heat will it not affect the cable, the fiber optic cable inside the which is in the core of the OPGW?
Hmm. It should affect actually. Okay. Okay, I'll think about it and I'll get back to you. Okay.
Yes, sir. Sir, one more final doubt, sir, for this
Hmm.
surge arrestor. In the
Hmm.
surge arrestor, we have zinc oxide.
Hmm.
Zinc oxide batteries or cells. Uh,
Yes.
Sir, once there is a flashover, once there is a surge, what do you say,
Hmm.
there is an overcurrent which the surge arrestor captures it and it grounds it. So then
Hmm.
there will be no effect on the zinc oxide. No properties of the zinc oxide will change because there are surge counters, and whenever there is surge, the surge arrestor activates. So on a repeated use, will there be no effect on this?
I could not get your question properly. Can you tell once again?
Yes, sir. Actually, I'm not framing it properly.
Hmm.
Sir, whenever there is a surge, there
Hmm.
will be a breakdown in the
Hmm.
zinc oxide. No, is
Hmm.
it like this?
Correct.
The operation of zinc oxide, surge arrestor is like this.
Hmm.
So a surge arrestor is designed so that uh, uh, it operates multiple times. That is the reason we also have a surge counter. So what I'm saying is, due to this repeated fault and repeated fault current being flown through the zinc oxide, will there not be any change in properties of the zinc oxide over a time?
Due to multiple faults, you are telling, will there be a change in the
Or
property of the
zinc oxide, like
I think you asked a similar question in the previous class also. Yes, actually, yes, obviously with time that zinc oxide surge arrestor will deteriorate and there will be an effect on the performance characteristics of the this thing. But yes, you have a particular lifetime for any equipment, right? So during that lifetime, it is assumed that it will perform perfectly and that small changes in the properties that is ignored. Yes.
Sir,
if there are any further doubts, I will
can I interrupt, sir?
Yes, yes. Yes, Mr. Raju. you can.
Sami's first question, whether the deduction part of it, any fault, the deduction part of it, it is done by CTs, PTs, and the relays.
Yes.
But especially in the high voltages, especially the high SF6 breakers, because of very high voltages, the bushings are there. The terminals are, it is with the bushings. In the bushings itself, it will be, the PTs will be there. PTs and CTs. And inside the relay also. So from there, it is a composite unit. That is the SF6 breakers. It may be a composite unit with the protection as well as clearing of the fault.
Okay, fine. I understood. Okay.
Okay, sir.
Okay. Anything else? Any clarifications? Anyone? Anything else? Any doubts? You can always reach me through email or the WhatsApp group. Yes, Mr. Anwar is there. He was messaged. No, he's not there. Okay, fine. So all of you are in that WhatsApp group, right? Yes, Anushri.
Yeah, I am there.
Yes, Anushri, you are
Good
raising
evening,
your
sir.
hand.
This is Mahesh Madan. I am not in the WhatsApp group.
Just a second, Mr. Mahesh. I'll answer Anushri. Yes, Anushri.
Sir, calculator will allow for exam for solving numericals.
That I am not actually aware. I'll ask and I'll inform you in the group. Okay.
Okay.
No, sir. Actually, the computer, the calculator are there. They can use the calculator inside the computer.
Okay, that is like
it's a
gate
scientific calculator.
examination.
They will allow it.
Okay, like gate examination, you will have a virtual calculator, I believe.
Virtual calculator, scientific virtual calculator.
Okay, okay. Okay, anything else, Anushri?
No, sir.
Okay, fine. You can lower your hand. Yes, Mr. Mahesh, you are telling something?
Good evening, sir. Sir, I'm not in the WhatsApp group. Actually, I was in US for 3 months and it is first session I am joining here.
Okay.
So I'll be grateful if you could add me in that.
Yes, you can access the chat section of this meeting.
Let me try.
Just check once and tell me. I will post my email ID. You can send me a this thing. You can ping me. I will add you in the group.
Yes, sir. I'm on chat section.
Okay, I have given my email ID there. Can you see it?
It is still trying to load that.
Okay, you can note down my email ID. I will tell it. It is Soumyadeep, SOUMYA.
1 moment.
Hello.
Sir, can you give me your email ID?
Yes, it is SOUMYA.
SOUMYA
DEEP, Soumyadeep,
DEEP, Soumyadeep. Yes, sir.
yeah, dot
Dot.
Chaudhary, CHOW,
Repeat, sir. Dot.
dot CHOW,
CHOW.
yeah, CHOW, DHURY,
DHURY. Chaudhary.
Chaudhary,
Soumyadeep dot Chaudhary
239
239
@gmail.com.
gmail.com. Thank you, sir.
Okay, you can just ping me here. I'll send you the link of the WhatsApp group. You can join. Fine.
Okay. Thank you, sir.
Okay, fine. Anything else, anyone? If there are no more questions, we will stop for today and we will meet next Saturday again 6 o'clock. Fine?
Sir, excuse me, sir.
Yes, yes.
Sir, if time permits, in any next class or at any time, kindly give a small discussion about transmission line protections, sir.
Okay, fine. I'll try to give transmission line protection, right?
Yes, sir.
Okay, sure.
Thank you, sir.
Okay, fine. Thank you, everyone. We will meet next Saturday, 6 o'clock again. Thank you.
Okay.
Thank you,
Thank you,
sir.
sir.
Thank you.
Good night.
Yeah.
Thank you, sir. Good night.